Good morning or good afternoon, depending on where you're joining us from today. My name is Chuck Tatham. I'm the Chief Marketing Officer at DENSIFY, and with me today is Dinesh Ravindran, one of our excellent cloud architects here at DENSIFY. And the topic today is all about leveraging Helm and associated frameworks to optimize container infrastructure resources. And along with that, we will be covering the input to that optimization, which is what DENSIFY does as part of this overall solution. From a administration perspective, you will see that there's the ability to ask a question through the console. We'd love to have your questions and comments. We will endeavor within the agenda, and I'll just pull that up. It's a very simple agenda. We'll endeavor to do Q&A at the end. We do have a prize today for those that stay through to the end of the session, a $100 Visa gift card, which is always fun to have. Our agenda is very straightforward. We're going to spend a little bit of time introducing what we see in our customers as some key management challenges around container infrastructure. We'll talk a bit about how DENSIFY helps you automate and optimize container resources, and then Dinesh will spend the balance of the time in both a live demo and as well sharing some architectural diagrams and some key concepts. So welcome, Dinesh, and we'll get right to it. So from a overall infrastructure resource and cost management perspective, what we're observing in the market is almost a sort of an aha moment where people are realizing that the old school way of thinking about infrastructure capacity is being shaken up at a pretty quick rate. No longer do you provision and procure and provision capacity like you might have in the virtualization days. With cloud and container and DevOps, you all of a sudden have many individuals potentially making micro resource decisions. And we say micro because they might be on a process or application level. We're not dealing in entire physical servers and an expensive box. You can distribute that decision making to, in some cases, hundreds of people. Many of those individuals are developers or application owners or business service owners, which leaves a high potential for uncontrolled risk and cost at scale. An individual might say, well, I'm going to make a decision on how much resource I want for my thing, and I don't really need to worry about the cost because it's small. But in aggregate and at scale, that can be a significant challenge. The other thing we're seeing is that when humans estimate or make best guesses or educated guesses, they're often not correct. So you have this sort of potential of, well, I'm not really worried about cost, I'm going to throw lots of resource, and I'm estimating how much something needs, and that's a potential risk point. Now, if you consider, and I don't intend anyone to read this diagram, if you consider the complexity of the matching of all the different types of supply elements that come into a container environment, the ways demand gets applied into that infrastructure, and the fact that it can be in many cases multi-tenant shared infrastructure, it becomes extremely complicated. I'll throw into the mix that a lot of the sophistication around virtualization, things like overcommit, don't exist in container environments. So we end up leaving a lot of this resource control, this decision making, to humans. At DENSIFY, we believe that to contain cost and risk, the majority of infrastructure resource decisions really need to be software driven. They can be empirically and software driven. That this requires an engine that can precisely determine the optimal type of resources and how to distribute them or assign them. And so what DENSIFY is, if you think of us as one thing, it's an analytics engine that will continuously and precisely optimize for these types of decisions. Now, over time, if you begin to realize DENSIFY can be trusted to come up with a very precise and accurate answer, at some point you're going to want to do something with that answer, and that's really the theme of today and what Dinesh is going to dive into. I will talk for a minute about how this engine works, though. We look at the challenge of really one of solving for multiple elements at the same time, and that is the individual container requirements, the node and scaling element of that, how those container resources are combined to deal with the demands that are placed on them, and then you have to figure in the cost and procurement side of it as well, because that's really important, especially if you're not doing this on-prem but in the cloud. And so it's our view that you can't optimize if you don't understand the impact of the individual container on the nodes and the scaling. You can't optimize purchasing and or the efficiency of the infrastructure if the nodes and scaling aren't correct. And you can't allocate container costs inside the organization if they don't understand things like the resource details and quotas. So you have to be able to solve for the union of these things, and that's what DENSIFY as an analytics engine does. It understands and learns from the behavioral patterns of the workloads or the processes to a very deep degree of detail. We understand the infrastructure attributes, where are you running, the cost, the performance, the technical constraints. We can associate tags and labeling so that you can apply that kind of decision making into the process. We do ingest billing data if you're running in public cloud. Then we have a policy engine that sets the guideposts for what is fit for purpose, safe and cost effective without offending any of these constraints. Now, this allows us to drive not only general visibility, everyone loves to understand what's going on in the infrastructure, but at the resource, container resource level, requests and limits, pods and deployment, scaling, clusters and namespaces, et cetera, initial resource values. When we get into scaling, the way you upsize and downsize, as well as understanding the financial side, the cost and procurement side. So what constantly comes out of DENSIFY are the optimal specifications. And now what I'm going to do is hand over to Dinesh, and he's going to talk about how you take those optimal specifications back into the infrastructure. So Dinesh, I'm going to make you presenter, and you should have it. Oh, you're muted still.
Thank you, Chuck.
You're good.
All right. Okay, cool. So I'm going to go ahead and start. Now I have a few slides to present, and once I complete these slides, we can jump over onto the demo. Okay, and I'm going to start here. This is actually a slide that leads directly off of the content that Chuck provided. It's a very high level slide, and it's going to talk to what do we mean by automation. And automation in the context of this webinar, specifically around how do we automate, or how do we inject the resource specifications that are coming out of the DENSIFY engine into a target environment, be it the infrastructure that controls the Kubernetes environment or the underlying containers that are running within that environment. And we believe there are three key pillars that are absolutely essential to driving automation in that context. Okay, so precision, transparency, and integration. I'm going to go through them. So the very, all right. So the very first thing here is we have the DENSIFY engine. It comes out and it generates a set of recommendations or insights. These insights now need to be automated. Now we can deliver these insights directly to the deployment arm of your CI/CD pipeline, or of the technology that's deploying the infrastructure or containers within that target environment. And how that's done is different for each of these technologies. So from an infrastructure perspective, we're talking about the nodes that are managing the underlying Kubernetes environment. So how do we do that? How do we actually drive that automation? Well, from a nodes perspective, from an infrastructure perspective, you're really utilizing infrastructure as code technologies to stand up this infrastructure and to manage that infrastructure. And therefore, we need to go through these technologies to deliver those recommendations, thereby ensuring that we do not introduce drift into that target environment. So this is a very simple, AWS EC2 example where we inject a DENSIFY recommendation directly into the IAC template. So in this particular case, you can see under the instance type parameter within the EC2 specification, we're saying instead of hard coding something like an M4 large or a specific instance type from AWS, we're saying look it up from DENSIFY directly or dynamically from an entity that's specified within the template itself. And that keeps it very, very dynamic. So whenever that infrastructure as code technology is called within your pipeline, it automatically references insights that are derived by DENSIFY at runtime. What about for the application layer? Well, it's different, right? For the applications that are deployed inside a Kubernetes environment, we're no longer using IAC technologies. We typically find package managers like Helm or Customize that's really at the forefront of that deployment, of that application deployment. So in this case, we're seeing a Helm command called install upgrade or template. And you guys, I'm sure you guys are familiar with Helm, but if you see this particular command, we're calling it with a keyword that's specified right before that command. It's optimized. So in this way, we're using a Helm plugin to really look up those insights prior to installing an application, upgrading an application, or templating it out. Okay. Now, we typically find these recommendations, although we can see this arrow is pointing directly to these end deployment arms, when we approach an organization, we don't typically find that they would implement a recommendation just because it's generated by the engine. They go through an official change management process. So this is why, alternatively, we can deliver these recommendations to an ITSM platform like a Jira or ServiceNow to go through their change management process to acquire the necessary approvals from the appropriate stakeholders prior to implementing those insights. So the actual engines at the front, at the rightmost component, the lookup plugin at the top and the optimize plugin at the bottom, they are reading two different inputs. One is the approval setting as well as the actual recommendation. So they will only implement an insight if it's approved by the organization. Okay, so in this way, we say that there's three components here: the precision of the DENSIFY engine, which is absolutely pertinent or important when it comes to automating recommendations, because unless it's precise, unless it's accurate, it cannot easily be automated at runtime in real time. Okay, the transparency is absolutely critical. I've been hard pressed to even find a single organization that will implement a recommendation without it going through a change management process, without acquiring the necessary approvals. So this is why we say transparency is the second pillar to this automation strategy. And finally, the integration that connects or interconnects all of these key components together to drive that automation. And that's why we say the three pillars of automation from this particular context is precision, transparency, and integration. Okay, and for the remainder of the session, these two arms at the rightmost corner here, we're only going to be focusing on the application layer. So we're going to look at container optimization, not at the infrastructure side. Okay. And how we're going to do that? You saw two technologies there, Helm and Customize. The purpose here is not to delve deeply into Helm or Customize and look into their nooks and crannies. We'll talk about them from a high level, but really we're trying to achieve three things. We're looking for technologies that we typically find being used as deployment technologies in Kubernetes environments. We're trying to understand common architectures that we typically run into that combine these two technologies. And once we have these common architectures, we look for a solution that will fit both of these together. And finally, we'll end off with a demo. Okay, so Helm. So what is Helm? Very high level. Again, I'm not getting into the details. What it essentially allows you to do is package different components or Kubernetes objects into an entity they call a Helm chart. And we can deliver these Helm charts to a public or private repo. What does this mean? If you look at your application, it comprises of multiple different components. You could have deployments, pods, cron job, various different components, security policies, profiles, and whatnot. And you want to sort of package all of these components into a single entity that you call your application. Now, Helm also allows you to package in dependencies. So for example, if your application is dependent on third-party libraries or other applications, you can define those applications within that Helm chart. So you have a single entity now, and in its entirety, it's your particular application. And you can now deploy it very easily in a target environment. You can share that application with others. So what I just defined here is the definition of a package manager. And that's exactly what Helm is. So in short, it's a package manager for Kubernetes. Okay, which brings us to some of its, in my opinion, some of its key value propositions. The first one being application management, which is really the package management capabilities that Helm provides. Also, the visibility that you gain once that application, the discovery that you gain once that application is deployed in the target environment. You can see which application is deployed, all of its components, as well as the complete historical context and its revision history as to what's deployed. Dependency management, again, as I've already said, right, you can include different dependent charts or components of that particular application in your chart itself. And lifecycle management, you can define how that application is deployed and how it's rolled back. I didn't catch that. Sorry. All right. And I also say that this is very practical for CI/CD integration. And we'll see. I know a lot of people here are going to argue that it may not be practical for CI/CD integration, particularly if you're talking about runtime configs like CRDs or sealed secrets or security context, annotations. How do we get those? How do we get that configuration into to Helm charts, which are primarily Go templated? And I would say that from a very simple perspective, if you're deploying a very simple app in a very simple environment, then it's very practical for CI/CD integration. I've seen it with organizations just using Helm alone. And we'll talk about the drawbacks of Helm in a moment here. So how do we call Helm high level? You simply, and by no means will someone in a production scenario, will someone actually log into a node and call Helm to deploy an app. This is typically done dynamically through a CI/CD pipeline. But for the purposes of today's session, I just wanted to describe how Helm would actually deploy that app. So in this case, you can call Helm via the simple Helm install or upgrade command. You can pass in whatever command you like. The subcommands for those two primary commands. Helm will go out, extract the specific chart that you're talking about, whether it's a locally sourced chart or from a repository. You pass in configuration to that chart. Remember, these Helm charts are Go templates, and therefore configuration for those Go templates are interpolated at runtime, either through your values.yaml file, which is your Helm YAML file that defines a configuration, or whatever you pass in through the CLI in that command. Okay, so once you pass those two commands in, you can also pass in additional values files or configuration files, specifically if you're deploying to, if you have very specific environments that you're deploying to. So say in this case, you have three different environments. You have a dev environment, a stage environment, and a production environment. You can define additional configuration value files that you would provide to Helm at runtime for those specific environments. Because let's face it, obviously each of these environments could definitely have different configuration, slightly different configuration to run, and therefore that's how you customize on top of the default. Okay, so high level, that's how Helm runs. And as I said before, there are drawbacks to this architecture. Particularly, I'm sure there's many different drawbacks, but in my opinion, there's three top ones. The first one really being the ongoing cost of maintenance. If you think about it, the Helm chart defines the actual application, and those charts are specified as Go templates. But what if you need to add additional context to it, some security context that's specific for your environments, some additional annotations that you want to add, CRDs? Then how do we get these implemented using a pure Helm-based approach? Well, you have to ensure that those Go templates actually contains provisions for you to interpolate those configurations in, and usually they don't exist, which means you're going to have to go into your Helm templates and add additional logic, and that's configuration and coding that you would have to do at the Helm level to ensure that those configurations are exposed to Helm such that you can now interpolate or add configuration to your values files or add them into CLI. And this is an ongoing effort, because you do it once for your first version. Imagine if there's a second version or second release that comes out, you're going to have to again fork your Helm template and make those same configuration changes again. It defeats the purpose of automated implementation. Okay, so from that perspective, it's that drawback exists. What about it from an abstraction perspective? if you have a security group within your organization that requires a specific security context to be added to certain Kubernetes objects that are running in your environment. Well, the only way to do it through Helm is to, again, ensure that it's exposed to the Helm chart or to the template. Now, developers are normally the ones that go in and actually ensure that that logic is added to those templates. So in that way, you're really exposing that security context to the development team. And finally, if you wanted to make a minute change across multiple pipelines from Helm, and it's just one change, I want to change a version of the specific container. From Helm's perspective, you would have to go in and ensure that values.yaml file has that configuration, and for you to make that change across every single pipeline. And again, if one of your applications or pipelines doesn't have that specific configuration, you have to go back and make that change to the template itself. So these are three things that I think that are key drawbacks for Helm. I'm sure there's others, but I wanted to leave it at that because when we go to the next technology, we're going to see how Kustomize can sort of overcome some of these challenges. Now, despite everything I said here, I still believe it's practical for CI/CD integration on its own for simple applications. So Kustomize, what is it high level? So it takes a slightly different approach to the deployment arm, in which case, and what I mean by that is instead of employing a templating technology, Kustomize relies on patching or overlaying configuration on your base KDS manifest file. So you have your manifest files that are already rendered, and you have the plain text output for your YAML files. Kustomize takes that as inputs to say which portions of those KDS manifest files do you want to replace or modify or add. And by doing it this way, you gain a lot of visibility and transparency because you have access to those KDS manifest files. You know specifically what's being deployed. It also, and I guess its larger value proposition is around the customization angle for all the real-time configurations that I mentioned in the downside pieces of Helm, where if you have specific security context or annotations that you wanted to customize on those original KDS manifest files, it's very easy to do with Kustomize. It's very effective from that particular perspective. And I'm going to just high level show you how it runs here. So essentially, if you're a user for Kustomize and that's all you have in your environment, you need to source or you need to create your KDS manifest files. They're your applications. You simply call Kustomize with build command to actually go ahead and begin the customization process for those manifests. And obviously, you need to provide some configuration data, and that comes into these customization files. So Kustomize takes this as input for each of your different environments to apply the necessary customizations on those target Kubernetes files before it finally deploys in the target environments. So again, this is very, so the key value prop here on Kustomize is that it's very effective when we talk about making runtime configuration changes on your applications prior to deployments. Things like, as I mentioned before, like CRDs, security context, annotations that you want to insert in sealed secrets. It becomes very, very simple. But in this mechanism here, I have not specified that I don't believe on its own is it practical for CI/CD integration. I'm sure if it's a very simple dev application, you're just testing out your specific container, you can use Kustomize to deploy it, and that's fine. It's a valid use case. But I've been hard pressed to run into organizations that just use Kustomize to deploy applications at scale in production environments, simply because it's lacking some of the undeniable capabilities that Helm brings, which is really around the application management. That packaging capability that Helm simply doesn't have. Okay, so which brings us to another architecture that we typically run into for more advanced organizations that are running more complex environments. They try to get around the limitations of Helm and Kustomize by combining the two technologies together and running them in series. So they take something called a template approach first, where you use Helm to render all of your charts. So you have your KDS manifest files, and then you can overlay or patch to those files using Kustomize for your runtime configurations. Okay, so in this way, you actually maintain the capabilities for application packaging and configuration. So you have all of your applications very easy to deploy. You can just say Helm install my app or Helm template my app, and Helm will go to the repository, grab all of the components, including your dependencies, and generate all of those KDS manifest files. And you're not going to compromise your transparency because you have visibility into those manifests. And obviously, because you're calling customize after that, you're able to inject real-time or runtime configurations like those CRDs and security context annotations and specific tweaks for environment-specific configurations towards the end of that chain. Okay, so this is why I say this is very practical for CI/CD integration. High level, how does it work? Someone's going to go out and instead of calling Helm install or upgrade, in this case, you're going to call Helm template, and template is going to just essentially render all of the charts and not perform any installation. So it's going to go out, it's going to pull the Helm chart, it's going to apply the default settings that you provide to Helm to go out and generate those KDS manifest files. And finally, you then call in customize to go ahead and build and apply the final runtime configuration customizations on those manifests. And we've seen this already. And it goes out to the 3 environments and it deploys. Okay, so 2 architectures that we ran into that I believe are practical, and we're looking for a solution that fits both. The first is a Helm only implementation, and the second is a Helm plus customized implementation. Okay, so high level solution. What are you guys going to see in the demo today and how it works? The first piece is let's remember why we're attending this webinar. The context of this webinar is really around how do we automate, densify optimal resource recommendations into target environments, into containers at runtime. So that's the primary use case here. So we start here with the DENSIFY optimization engine, and we're going to generate a set of recommendations. And how we do that by auditing a target Kubernetes environment. We do this through Prometheus to pull resource utilization metrics. So we analyze the underlying CPU, memory, disk. Now, all of the different low-level metrics that are required to understand the performance and behavior of that container, of the underlying containers, we extract through Prometheus to go through our analysis engine to generate out insights to say, hey, these specific containers would do better from a performance perspective and a cost perspective if they ran with these particular resource specifications. So once we understand what these resource specifications are, we expose them to any environment through our insight repository layer. Okay, and finally, you're ready to now implement. So Helm can now be called in an install case or an upgrade case, or template in the case where you want to go to customize. So if you call Helm to install this application or upgrade this application, obviously it would be an upgrade scenario. Helm would go out, pull the next revision of that chart, would apply the values.yaml file, which is your configuration that it's now going to interpolate into those Go templates. But in that process, it's also going to interpolate in the new updated resource specifications that are coming from that Insight repository. And it does this by way of a plugin. This is a standard Helm plugin that gets deployed on the system as well. And it's invoked by calling the keyword optimize right before the your install, upgrade, or template command. The install, upgrade, or template command does not change in any way. It's just simply called the full command is called by ensuring the optimized keyword is included as part of that command. So once that occurs, then Helm will render those charts with those resource specifications injected in. And finally, those newly generated charts are either deployed directly to Kubernetes, or alternatively, you can go to customize to perform any final customizations on those runtime configs before it gets deployed into that target environment. Okay. Last slide. A few comments here on the specific plugin. I'm going to be starting from scratch from the demo, so we'll go through the installation process. We'll look at the application. We'll try to optimize it using the plugin. And it's open source. It's available at this particular link, this GitHub repo. You can go in and you can check out all the different details behind this plugin. There's installation instructions as well as how the specific plugin works in this particular location. We'll provide the link towards the end of the session as well, so you don't have to copy.
Hey, we will also send out the recording so people will have this available.
Yeah. As I said before, it's a standard Helm plugin. It's built in Go, and it's responsible for nothing more than extracting insights from that Insight repository, whether it's DENSIFY or in the next part of this webinar, this series, from an ITSM platform like ServiceNow or Jira if you're going through a change management approval process. And I said before in the previous slide, you simply invoke the plugin by calling the keyword optimize in front of your standard command. No other changes are required. And I underscore this because we really want to emphasize that no additional configuration is required to make this work. You don't have to provide changes to your templates, your values, your CLI inputs. Your actual command, the install, upgrade, or template command remains as is. However you're running it today, it will accept it. It's capable of recognizing inside approvals, obviously, so it's not going to inject anything that is not approved. It will only work with approved recommendations. So in that inside repository has to sit both the recommendation and the approval in order for the plugin to provide that recommendation to Helm for the rendering process. There is one small capability we put into the plugin, which is the ability to approve insights in DENSIFY. And this is not meant to be used in production or at scale. It's simply for demonstration purposes. From a production perspective, all the organizations that we work with, again, I said before, go through a change management process to manage their approvals, and that's how we would implement it in production. But from a demonstration perspective, it's very easy for us to show how this works just by using a CLI function to execute that approval and then rerunning the upgrade command to show that it's now injecting the recommendation because it's approved. It's lightweight, said before, no config files, everything is through the CLI, and it's supported on Linux, Windows, and Mac. Okay, so with that, I'm going to go ahead and start the demo. Okay, and I hope everyone is going to be able to see my screen because I'm going to have two pieces open here. Okay, so the demo here, so on the left side of the screen over here, what you're looking at here is the DENSIFY console, and I'm sorry about the resolution. I'm trying to show two screens at once, so I sort of zoomed in on both sides just so you guys can see what's actually written there. So this is the DENSIFY console, and we're under the containers menu option, which is showing recommendations for the containers that we have audited on this particular instance of DENSIFY. And I've zoomed in to a very specific cluster with a very specific namespace, and I'm only looking at deployments. And the reason for this is we're only going to look at a very specific app that's running in the target environment. And the purpose of this demonstration, demo again, isn't to show that the app is actually working. It's just to ensure that we can inject these recommendations for any of these objects directly into an app. Okay, so on the CLI side over here, I have a Kubernetes environment running with nothing in it. So it's completely empty. So you can see here it's an empty environment. There's a couple of clusters that are running in this environment, and we're only going to be focused on one cluster, the EKS pre-prod US East 2, which happens to be the same cluster that we're looking at here in the DENSIFY console. And just to show you, the current context is also set to that. So we are in that specific cluster. Now the cluster contains two namespaces that we're interested in. The application, I'm going to say, is going to contain only two of these deployment objects. The first being this one that's sitting under the default namespace. It's called NFS deployment. And the second one is sitting inside the EKS ops demo environment, and it's called environment deployment. Okay, so I'm just going to show you guys what's sitting in the EKS ops demo namespace, and there's nothing, no resources sitting there. Okay, so I'm going to show the chart. So we have a very simple chart. Again, the chart doesn't really, it doesn't deploy a functional application. It's going to deploy a bunch of components, and we're going to see if we can inject recommendations into those components. So I'm going to cat the values file that we talked about. This contains all of the configuration. There's a bunch here, but what we're interested in here is the configuration right towards the bottom over here, which specifies the resource specifications for the different containers running in this environment, in this application. So there are two resources with 3 containers. So the first resource is a deployment resource. Right over here, we have deployment resource under the default namespace, and it's got a container named NFS. And right now, the resource specification is null. We're not going to specify any resources. So if we were to deploy this application using Helm, Helm is going to deploy it with no resources specified for its underlying container. So it would be completely blank. The second deployment object over here is called environment deployment. That's why it's got the same name here twice. It's one deployment object, but it's got two different containers. The first container is named environment. The second container is ISTO proxy. So over here, for ISTO proxy, we have a resource specification that's specified here. You know, limits 2,000 millicores, memory 1024 megabytes, and so on. And for the environment container, we have a resource specification here for limits and resources as well that will specify. And right now, the defaults are set to, you know, what DENSIFY has audited. So over here for the NFS deployment, it's blanked out because nothing's been specified. For the ISTO proxy, wait, I lost where ISTO proxy is right there. For ISTO proxy, it's specified as, you know, wait, sorry. Let's make sure I've got the right one here. Environment, we'll look at the environment. For environment, you've got, you know, 250 millicores, and the limits are 250 millicores, 1024 and 2048, which is what's specified over here in this configuration. Okay, so
those values are empirically derived from watching the infrastructure, not what someone has specified.
So the current value, the values you're looking at here in the CLI, this is something that someone's hard coded in to the templates, which is what we're seeing here under the current. Yeah. Right? DENSIFY is the recommendations over here, and this is what we want to implement. But we're going to start this process by just deploying this application and seeing what's running in the environment. So if someone were to deploy this application using Helm, okay, that's the chart. We're simply going to call Helm Helm install. I'll call it chart. And Helm is going to go out and it's installed the application. So if I go kubectl get all, we're going to see a bunch of components here running in the default namespace, because that's the default namespace that we're running in. If we were to query the NFS deployment, which happens to be the NFS resources, so I go kubectl describe deployment, NFS deployment. We're going to go down, we'll look at the pod templates under NFS, which is the name of the container. It happens to be the same name over here, container name. We'll see that there's no resource specifications that have been specified, simply because in the values file, we submitted null entry for the resource specification. So Helm interpolated null into the final Go templates. If we look at the other deployment, so kubectl get all namespace EKS ops. What is it? EKS ops demo. If you look at the other deployment, we have an environment deployment object running in there. So let's go ahead and look at what's deployed in there. So kubectl describe deployment, namespace EKS ops demo. And over here in this particular deployment object, we're going to see two containers running. As we noted before, there are two containers, environment and ISTO proxy. And these two containers have the resource specifications specified, which happens to be the same that we see under the current tab over here, and what's specified in the values.yaml file that we injected into Helm. So right now it's running with the default settings with the current settings. So DENSIFY is integrated into this environment. We've audited the environment, we've analyzed it, we've generated a bunch of recommendations, and we want to now inject these recommendations on an upgrade of this application. So how do we do it? The first step is really to install the plugin. You got to go through the installation procedure, otherwise there's no plugin for you to invoke. If I run Helm, I just want to show you guys the setup command before I actually install it. These are the setup commands that are available to Helm today. And we're going to show a new command becoming available once we install the plugin. So how do we install the plugin? Well, you're going to go to the GitHub repo, you're going to copy the link, right? Go back, and you're going to issue one command to install, which is Helm plugin install, and pass the path to the repo, enter. And we can see right now that the plugin is now installed. There's the help file here that tells you a little bit about the plugin and some of its capabilities. If I type in Helm again, just to see the list of commands, we can see a new command that's become available for Helm, which is now optimized. So optimize the performance of the release. So this is the plugin that's now available. If we want to upgrade this application, we're simply going to go and call Helm optimize, right? Upgrade, and you pass in your standard upgrade or install command or what have you. So over here, I'm just going to pass in a very simple command for a locally sourced chart. You could provide a command for a repo chart, whatnot, but we'll go ahead and run it. So this is the very first time I'm running it. And what's happening right now is the plugin it needs to understand where the specific DENSIFY instance is. Where is your repository? So it went ahead and then actually interpolated out the repository location. So you can see here k13densifydemo.com, 30,000. So it's done this because DENSIFY has originally integrated to this Kubernetes environment to extract the workload metrics. So the way we do that is by deploying a folder object that interrogates Prometheus within your environment. So the plugin actually works with that folder object. It goes to the folder and says, what is the current configuration for the DENSIFY environment? And that comes back and says, it's running under K13. So we know what the specific URL is. So we ask the user, is this the correct URL or is there a different URL? If they say it is, then you have to specify username and password. Okay. So once you specify the username and password, it goes ahead and performs the upgrade. So let's look at the outputs that we're actually seeing. This is, I wanted to zoom out here a bit because, okay, that's a little bit better. I hope you guys can still see. So there's a couple of differences here in the execution. If you look at the bottom here, this is a normal Helm output. At the top here, we're seeing the plugin output, which essentially is going to go through every single chart that you have, within your, all the different components you have within your Helm chart. So for this particular one, it's going to go through and say, hey, I've identified a container. It's running under the default namespace. Its object type is deployment. Its object name is NFS deployment, which is the deployment name. And the underlying container name is NFS. And it's going and saying, I'm getting invalid resource specs from the repository. Why? Because right now, DENSIFY is configured null for the current specifications. So it's not finding it because it's not approved. It's reading the current settings and it's finding null there. So it's saying it's invalid. It's checking the cluster to say, okay, it's because I can't find something from the repository. Let me go to the cluster to see what the resource specs are. And it's saying it could not find it in the cluster because, again, the object is running in the cluster with null settings. And it's saying it's checking the default settings provided either through values or through additional customizations if you provide it through CLI. And it's saying no default configs are present for this particular object, which is fair. That's the correct behavior. The second one over here, it's saying I've identified another two objects that are running under the EKS ops demo namespace. Object type is deployment. Object name is environment deployment. The first container is ISTO proxy. We can see that it's not approved in DENSIFY. It's not been approved, and its current settings are so. There's an environment container as well. It's not approved, and its current settings are so. And therefore, that's what we're going to implement. We're not going to make any changes to the running containers. And so let's go ahead and actually do that. So if I go kubectl, describe deployment, and let's look at that deployment to ensure that DENSIFY has not made any changes to it. Under namespace EKS ops demo, we can actually go back and see that the limits and requests for both containers remain as they were defined in the original values.yaml file. Because although we have access to the recommendation, we're not implementing it simply because it hasn't been approved. Okay, so the next step really is, okay, so we're going to have to go and approve these recommendations before the plugin will accept them and implement them. So there's many ways to do it. Again, in a production scenario, we're going to go through an ITSM integration to acquire that approval. DENSIFY manages approvals as well, but it's sitting deep within the system and it's not exposed to this front end right now. So a very simple way of approving the recommendation in DENSIFY, we built it right into the plugin. We're just simply going to call Helm optimize, pass in the flag -a, and you can grab this from, if you just plug in the help keyword for the optimize plugin, it's going to come in and say you can actually start approving your recommendation just by providing the -a parameter. So if we go Helm optimize -a, and we provide a path to the chart that we have, and then the plugin is going to go through each of your objects and say, I found this object in your repository. It's not approved. Would you like to approve it? I'm going to go yes if I want to approve it. I found this object. It's not approved. Do you want to approve it? Do you want to approve it? So right now, these three recommendations are sitting in the approved state within the Insight repository. So presumably, if I run the Helm upgrade command again, it should implement the recommendations from DENSIFY. Okay, so in the first case over here in the NFS, we're seeing the recommended request being 10 millicores, the limits being 10 millicores, and memory 850 to 940. Okay, so let's try this again. Helm optimize upgrade chart. Okay, we run that again. Okay, so the outputs look very different now. So under chart, build a chart for the very first container, we can see it's sitting in the approved state, and the new recommendations 10 millicores, 850 to 940, which happen to be the recommendation that's sitting inside the DENSIFY engine. Similarly, for the other two containers running in the other deployment object, we can see the DENSIFY recommendation, what we specified here, are being now passed in to these objects. So let's do a quick test. So let's describe the deployment for the very first object, NFS, to see if Helm has now implemented these changes. So if I go describe deployment, NFS deployment, we're in the default namespace, so I don't have to provide anything. We could see the NFS container now having the limits and requests, the resource specifications that are recommended by DENSIFY because it's been approved. So it was that simple for us to inject these recommendations directly into that target environment. So if you have a CI/CD pipeline that's relying on Helm to deploy your applications or Helm plus customize, it's very easy for us to just go in and say, hey, for that Helm install command, just install this plugin, and instead of just going Helm install or Helm upgrade, simply call Helm optimize upgrade, and we can very easily inject these recommendations in. And just the Helm optimize template command in the case you're using customize. So if you were to go template, go chart, it's going to do the same thing. The charts are going to be rendered using the same logic. So over here, under that very first deployment object, you have the two containers, I believe. You're going to see that they are rendered with the DENSIFY recommendations built right in. And similarly for the NFS object, we're seeing the recommendations in the output render files.
Dinesh, just as we wrap here, the question: if the repo is down, does the plugin implement default settings?
If the repo is down, right. So if the repo is down, it absolutely does implement. Well, what it does is it first checks to see whether the application is running in the target Kubernetes environment. If it is, then we'll maintain that configuration and will not touch it. But if there's no application running in that target environment, in the case of an install command, then it will implement the defaults that are specified in your values file.
And if another question, if someone does something through the command line, does it override, or what does it do?
If you specify any additional customizations through your command line, then it will override the values in your YAML file, in your values.yaml file. So it's your standard behavior that you would expect from Helm. So if you specify additional defaults, you say you have your values files and you specify defaults there, but you want to specify some additional overriding defaults when you call that Helm install or upgrade command to CLI, then we'll prioritize the commands that are provided through CLI because it's intended to override.
Okay. So can you go to the slide? Thanks, and if there's something I take away from what you've shown is that these environments are extremely flexible and it's a very powerful construct, but you can see the high potential for human error. Even if you're not considering the resource accuracy, resource specification accuracy, just by using it, we're jumping around a lot there, Dinesh.
I don't know why I'm saying that.
Just removing the uncertainty around the derivation of the resource specifications is a huge thing, and if we can pass them through these standardized frameworks like you've prototyped here, you could see the great power of that in a larger scaled infrastructure. So thanks very much, Dinesh, for taking us through that.
I also want to this webinar that you guys seen here today is part of a 3-part series. So the first one is on Helm. The second piece, we're going to look at ITSM integration with this particular plugin. to see how we can do this from a production at scale perspective. And then finally, we'll look at how do we integrate this very easily into a CI/CD pipeline using Jenkins or whatnot. So stay tuned for that.
Excellent. So without further ado, the selected individual from the draw is a Smita M as the winner for today of the $100 Visa gift card. We will be reaching out to you, Smita, to track you down and provide that prize. So thank you everyone for attending today and your attention. Please follow up with us through the DENSIFY website if you'd like contact or a trial. And thank you again, Dinesh, for taking us through that very interesting content.
Thank you.
Everyone, have a great day, and talk to you soon.